So in this video, I am going to just walk you quick through the answer key to our study guide. So up here, looking at the two diagrams, label which type of bond they have. The first one is going to be covalent. So because you can see they are sharing these 4 electrons here. Second one is going to be ionic. The electron is going all the way over to the chlorine. So the chlorine is taking it from the sodium. Number 2, draw hydrogen bonds between at least 4 water molecules and explain why hydrogen bonding occurs between the water molecules. So we have our 4 water molecules here, 1, 2, 3, 4. I have my dotted lines as my hydrogen bonds. So you can see that our hydrogen bonds always happen between a hydrogen and an oxygen of opposite water molecules. So between our partial positive and our partial negative. So water or hydrogen bonds occur, or H bonds occur, because of the partial positive charge on the hydrogen and the partial negative charge on oxygen. And during or when our hydrogen bonds are by themselves, so when they are alone, they are weak. It is only when we have a bunch of hydrogen bonds together that they become strong. Yeah, number 3, this is going to be a hydrolysis reaction. We can tell that it is a hydrolysis reaction because our products has water, so H2O, so we're using water, and we end up with 2 monomers here. So we start with a polymer and we end with 2 monomers. So that's how we can tell that it is hydrolysis. A paperclip floats on top of water. What property of water causes this to happen? So this is going to be cohesion. So water is bonding to water. And that happens because water forms hydrogen bonds with each other and it creates that surface tension that holds the paperclip on the surface of the water. For the following properties of water, discuss how it helps organisms survive. So what I talked about is water's 3 states of matter. So ice, and it's in water solid form, which is ice, is less dense than water. So that means it floats, which is a little bit different than almost every other substance. Normally, the solid version of a substance is going to be more dense than the liquid and it will sink. But ice floats, so this allows organisms in bodies of water, such as lakes or rivers that freeze over during the winter, to live throughout the winters because the ice stays at the top of the body of water rather than sinking down to the bottom. Water is polar, so that allows it to become a universal solvent. So our universal solvent is going to help organisms take in different nutrients such as like minerals and vitamins that they need in their system because they will be dissolved in our water. Next, our table up here. So we have protein, carbohydrate, lipid, nucleic acid across the top. Our protein monomer is going to be an amino acid. Our polymer is going to be a polypeptide, and our bond is going to be a peptide bond. Our carbohydrate, our monomer is going to be a monosaccharide. Our polysaccharide is going to be a polymer, and glycosidic bonds are our bond type. Lipids, remember lipids don't have monomers or polymers, and they are made of ester bonds. Nucleic acids, our monomer is going to be nucleotides. Our polymer is going to be nucleic acid, and we have phosphodiester bonds. So our next question is going to be, if a polysaccharide is being cleaved or cut into monosaccharides, what type of reaction, dehydration or hydrolysis would it be? So this is going to be hydrolysis, right? So hydrolysis is a process of breaking apart a bond using a water molecule. So we're breaking apart our polymer into monomers, right? Water or hydrolysis. If we break it down, hydro, water, lysis, cut. So water cutting. So when we're looking at this next question, so in protein folding, what is primary structure, secondary, tertiary, quaternary structure, and what interactions causes these structures? So our primary structure is going to be the sequence of amino acids. Our secondary structure is going to be beta pleated sheets or alpha helix, and those interactions are going to be, or they're going to be caused by our hydrogen bond interactions. Tertiary structure is going to be when the polypeptide starts to fold on itself, and that's going to be R group interactions. Then quaternary structure is going to be when 1 or more polypeptides come together, and those are going to be held together once again with hydrogen bonds. Looking at our different images down here, labeling our biomolecules. So we have our lipid, which you can tell it's a lipid because it has a long hydrocarbon chain. Our carbohydrate, which has a ring structure made of carbon, hydrogen, and oxygen. Nucleic acid, which has our phosphate group and our nitrogen base on it. And then our protein, which has our amino group, our R group, and our carboxyl group. Next, looking at the graph below, so look at this graph here. Is it showing endergonic or exergonic reaction? How do you know? And would delta G be positive or negative? So this is going to be an exergonic reaction because there's a release of energy. We can tell that there's a release of energy because A, it says energy released, and B, our reactants have higher energy than our products. So that means we are releasing energy. And if we are releasing energy, we are going to have a negative delta G, right? So then exergonic reactions will always have a negative delta G. Another way to look at it is delta G is going to be taking basically our products minus our reactants here. On the Gibbs free energy diagram, so on this diagram here, draw a line where what the reaction would look like if enzymes were added to it. So when you're drawing this line, you want to make sure that your reactants and products are at the same. And the only thing that changes is our amount of activation energy needed, right? The enzyme will only change or alter the amount of activation energy needed. It will not change the delta G. So our reactants and products should be the same for each line, and our activation energy is only going to be, or is going to be the only thing that changes. Our next page, explain what coupled reactions mean, why is it beneficial, and how does ADP to ATP and reverse a coupled reaction. So coupled reactions are ones that happen at the same time in order to use energy more efficiently. So one reaction will produce energy, meaning it is going to be exergonic, and another reaction will use energy, which it will be endergonic, right? So we're gonna have one endergonic and one exergonic reaction working together. So up here, I kind of ran out of room because my handwriting's kind of big. So ATP to ADP will release energy, right? Because we're breaking that bond off, and that energy can then be used to phosphorylate. So add another phosphate to a different ADP, creating ATP. So our energy that is released from our first reaction will be used to further our second reaction. Next, draw and label an enzyme, substrate, active site, allosteric site, competitive inhibitor, and non-competitive inhibitor. So we have our enzyme. Our allosteric site is going to be off to the side, and our active site is going to be where our substrate binds. So right, our substrate is going to be what our enzyme works on. The substrate's going to bond in there. Here I drew a competitive inhibitor. It is bonding to our active site and blocking it so our substrate can't fit in. And our allosteric or non-competitive, those are the same thing. Inhibitor here in purple is going to be that little triangle shape. So it's going to change our shape of the enzyme so it would become that dotted line V shape, right? And so that is going to be our allosteric. Number 2 on this page, looking at the graph below, which number 1, 2, or 3 best represents an enzyme that lives in a hot spring where temperatures reach 70 degrees Celsius or higher? So if we're looking at these, we want to look and see which one is going to work the most or like have the highest rate of reaction in those high temperatures. So if we look at about 70 degrees, if we go up here, we can see that number 1 and number 2 are not functioning at all. So that means those enzymes, the proteins in those enzymes are going to be completely denatured at that heat and will not work. So that means that number 3 is going to be our enzyme that lives in hot springs. And like I said, it peaks around 80 degrees Celsius, which shows that the enzyme would still work and would not be denatured by the amount of heat. Our second law of thermodynamics is everything is in a constant state towards entropy, and and life does not violate that second law because all reactions that are spontaneous will always increase entropy, right? So we're going to always increase our entropy spontaneously, and we will need more energy. We'll need to put energy in if we are decreasing entropy. Calculate the rate of enzyme reaction for the graph. So for this one, for 2A, between pH 7 and pH 10. So pH 7 is going to be right here. This is going to be pH 7, and then we have pH 10. So what we're going to do is we're going to take rise over run. So we're going to do y2 minus y1 divided by x2 minus x1. So over here, I have 0.16 minus 0.15 divided by divided by 10 minus 7. And that's going to give us 0.0033. If I do the same thing for pH of 4 and 7, we're going to get 0.03 as our rate of reaction. And then down here, we have our activation energy on both graphs, which are going to be up in our hump. And then this is going to be energy being absorbed and energy being released. So because energy is being released, this is going to be our exergonic reaction, and this one is going to be our endergonic reaction because energy is being absorbed. I think this is the last question. What are reasons a reaction would reach Vmax, and what are reasons a reaction would come to a complete stop? So Vmax, if it was saturated with a substrate, or so like our substrates would always have a ton of enzymes, or our enzymes would always have a bunch of substrate to react with. It would come to a complete stop if we had like an irreversible inhibitor or just a saturation of inhibitors. So anything that would stop our enzymes from working. So that is our review guide, our review packet for this unit. So if you have any questions, feel free to shoot me an email and I will try my best to help you.